So in the last video, a few videos, we've been looking at the concept of interference, essentially when there's multiple waves in a medium, and we use this principle of superposition where the total displacement from all the waves is just the sum of the individual wave displacements. And in the last video, we looked at what happened if we had two waves in a given medium, described by displacement one and displacement two, that were we looked at the example of, say, speakers playing the same note, right? So they had the same wavelength and frequency, so the Ks were the same. The speakers could be either in phase or out of phase, the actual oscillators creating the sound. But what happens when we have two sinusoidal waves like that in the same medium? And what we did is we derived that the total displacement due to those waves went like this. It created essentially another sinusoidal wave with an amplitude that varied depending on the phase difference, where we had the phase, the argument of that sign for wave one, and the phase of wave two. And the difference in phase between those two, or the phase difference divided by two, caused this amplitude to either be really large if we had crests lining up with crests from the two waves, or we could have the case of perfectly destructive interference where we would have a crest from one wave lining up with a trough from another wave such that they would cancel, and you would have essentially no wave. You'd have zero amplitude here. And when we looked at that, the results were essentially for maximally constructive interference, essentially the sine wave with the largest amplitude we could have, twice the individual amplitudes of the two waves that were interfering. We needed that phase difference to be some multiple of 2 pi. Essentially, if it was all just a path length difference between the sources and the observer, we needed that to be some multiple of a wavelength. For perfectly destructive interference, we had a different condition where this cosine term would go to 0, provided that the phase difference of those two waves was some m plus 1/2 times 2 pi phase difference, and that would result in crests aligning with troughs and perfectly canceling, such that there's no real amplitude to that wave, or essentially no disturbance. What we're going to do today is, this was the example where we had two sources that had the same frequency interfering with each other. We're going to do one final type of interference. We're going to look at what happens if those frequencies are different. So we have two different frequencies, or two different sources of waves that are oscillating at different frequencies. So how does that work? Well, they're both going to be described, if we have two sources let's go back to the speaker example. Let's say we have two speakers in a room playing two notes that are really close to each other, just slightly different frequencies. We have they're described both by these sine waves, except for we're going to have omega 1 and omega 2, because those frequencies are going to be slightly different. And the math, when we add them together, gets us the same result, where we're going to have some sinusoidal wave with an amplitude that depends on the phase difference. But what's the difference now? Like the thing that's new in the the sources are operating at different frequencies, is that phase difference is, well, it's going to be K1 x1 minus omega 1 t plus the phase constant for that first source minus the phase of the second source, which, K2 x2 minus omega 2 t plus the phase constant of the second source. And if we look at this, well, we're going to have a bunch of different terms here. We're going to have K1 x1 minus K2 x2 plus some phase constant of the first one minus the phase constant of the second source. All of these terms, these are constant in time. So we have, this term, this term, this term, and this term are all time independent. They're going to have some phase difference. It's only going to depend on where you are in the room listening to those speakers and what the wavelength of those notes are. But then we have this other term from the different frequencies that's going to give us minus omega 1 minus omega 2 times t. And this term, this varies with time. So what does that mean? That means that this amplitude, this is essentially some amplitude for this sine wave, is going to vary with time. We're going to see it cycle through. If we plot that amplitude as a function of time, if this is cosine delta phi over 2, it's going to go something like this and oscillate up and down. And essentially, the sound we hear, it's going to be proportional to that amplitude squared. It's going to go from loud to quiet, and then get loud again, and quiet again, and loud and quiet, and loud and quiet. And it's going to pulse and sort of modulate in and out and in and out and in and out. So if we look at that term, we have this cosine delta phi over 2 term right here in our amplitude, and that's going to go as cosine omega 1 minus omega 2 over 2 times t, right? So this is going to oscillate with some angular frequency omega mod that is going to be omega 1 minus omega 2 over 2, right? Or if we wanted to do that in terms of frequency, we would just divide, the modulation frequency is going to be equal to the modulation angular frequency divided by 2 pi, which, divide everything by 2 pi here. And this is just going to be f1 minus f2 over 2 is that modulation frequency. And, what that essentially means is the period sort of this amplitude modulation going from here to here, that period is 1 over that modulation frequency. So that sort of describes the interference pattern, but if we want to describe what we would actually hear, you end up with this loud, then quiet, then loud, then quiet, then loud. We have the frequency of what we call the beat. So we call this phenomenon beating, where if you have two frequencies that are, or two speakers, say, that are playing a note that's close together in frequency but not the same, the strength or the how loud that sound you hear is going to go from loud to quiet, loud to quiet, loud to quiet. We call that beating, and the frequency of the beat is twice the frequency of that modulation, which ends up being just f1 minus f2, or the difference in frequency between the two sources. Now, to give you sort of a visualization, because it's hard to really come about this without speakers in hand. Unfortunately, I don't have them. If we were in person, there's, again, tons of really interesting demos you can do with this, but we have a sign. If you look at what the wave pattern actually looks like when we take these two frequencies and add them together, you get this sort of, in blue here, this sinusoidal wave like we'd expect, but the amplitude of it varies with this modulation, right? That's due to that cosine, the phase difference over 2, which is time dependent and varies because of what we just went through. And because the difference in frequency between the two sources. And when the amplitude's large, we have it loud, then quiet, loud, quiet, loud. And the frequency with which this happens is just proportional to the difference in frequencies between the two sources. Now, there are a lot of excellent videos. You can, just search YouTube or Google, beat demonstrations or interference in beats, and you'll see tons of examples of this in class. In person, you can bring in tuning forks and speakers and do a bunch of things. Here is a link to one from, I believe, Columbia Science that I found. Goes through a bunch of just examples of beats and a kind of a rough explanation of them. Please watch that. That's the last thing we're going to cover for this semester, going into the exam. Again, click on that link so you get sort of a better, audio presentation of what beats actually are. If you have questions about all this, interference phenomena, waves, bring it up in the synchronous sessions, email me. We're going to be having some discussions and working through some examples and problems of this in class. So I will see you then. I hope these videos have helped you learn and that you enjoyed the semester.